Hey everyone, and welcome back to the channel. Today we're diving deep into a fascinating problem that bridges algebra and number theory. It's the kind of question that looks simple at first glance, but has some really cool layers to unpack. So grab your notebooks and let's get started. Here's the problem we're going to tackle. Find all positive integers n for which n cubed minus 14 north squared plus 64 north minus 91 is a prime number. Wow, that's a mouthful. Let's call our expression p of n. So p of n equals n cubed minus 14 north squared plus 64 north minus 91. Our goal is to find the integer values of n that make this whole thing a prime number. So, where do we even begin with a cubic polynomial like this? A good first step when you're dealing with polynomials and looking for integer solutions is to see if we can factor it. If we can break it down into smaller pieces, it becomes much easier to manage. To factor a cubic, we can use the rational root theorem. This theorem tells us that if there's a rational root, it must be a divisor of the constant term, which in our case is negative 91. Let's list the divisors of 91. Well, 91 is 7 times 13, so the divisors are plus or minus 1, plus or minus 7, plus or minus 13, and plus or minus 91. We need to test these values by plugging them into our polynomial, p of n, to see if any of them give us 0. If p of some number a is 0, then n minus a is a factor. Let's start with the easiest one. N equals 1. Plugging it in, let's try the next divisor. N equals 7. P of 7 is 7 cubed minus 14 times 7 squared plus 64 times 7 minus 91. Now, 7 cubed is 343. 14 times 7 squared is 14 times 49. A quick calculation, 14 times 50 is 700. So 14 times 49 is 700 minus 14, which is 686. So we have 343 minus 686. Next, 64 times 7. 60 times 7 is 420. 4 times 7 is 28. So that's 448. Our expression is 343 minus 686 plus 448 minus 91. Let us add the positive terms. 343 plus 448 is 791, and the negative terms, negative 686 minus 91 is negative 777. So, we have 791 minus 777. Oh, wait, let's recheck that calculation. 343 plus 448 is 791, and 686 plus 91 is 777. So, 791 minus 777 is 14. Still not 0. I might have made a small arithmetic error somewhere. Let's double check the 14 times 49. 10 times 49 is 490. 4 times 49 is 196.490, plus 196 is 686. That's correct. Let's look at the expression for n equals 7. P of 7 equals 7 cubed minus 14 times 7 squared plus 64 times 7 minus 91. Notice that 14 is 2 times 7. So the second term is 2 times 7 squared, which is 2 times 7 cubed, and 91 is 7 times 13. So we can factor out a 7 from every term except the first one. Wait, let me rephrase. Let's look at the numbers. 7 cubed is 343. 14 times 7 squared is 14 times 49, which is 686. 64 times 7 is 448. And we have minus 91. So 343 minus 686 plus 448 minus 91. Let's combine them differently. 343 plus 448 is 791, minus 686 is 105, and 105 minus 91 is 14. Okay, so P of 7 is 14, not 0. Maybe I made a mistake in my initial assumption. Let's try another divisor. How about 13? No, that's getting big. Let's rethink. Sometimes the problem setter hides a clue. The number 91 is 7 times 13. Maybe one of those is a root. I am pretty sure I am close with 7. Let's recalculate one more time, very carefully. Let's try to be clever. What if the expression can be factored in a way that involves n7? Let's try synthetic division with n equals 7 and see what the remainder is. Our coefficients are 1, minus 14, 64, and minus 91. Bring down the 1. 7 times 1 is 7. Add it to minus 14, we get minus 7. 7 times minus 7 is minus 49. Add it to 64, we get 15. 7 times 15 is 105. Add it to minus 91, we get 14. The remainder is 14, which matches our calculation. So, P of n divided by n minus 7 gives a quotient of n squared minus 7 north plus 15 with a remainder of 14. This means P of n can be written as n minus 7 times n squared minus 7 north plus 15 plus 14. This doesn't look like a direct factorization. Let's take a step back. What if I copied the problem wrong? Let me check. N cubed minus 14 north squared plus 64 north minus 91. No, that's correct. Maybe the root is not an integer. Wait, let's look at the expression we got. N minus 7, NA7 north plus 15 plus 14. This is interesting. Let's call the quadratic part Q of n. So Q of n is n squared minus 7 north plus 15. Let's analyze this quadratic part. Okay, back to our main expression. P of n equals n27 asterisk qn plus 14. We want this to be a prime number. Let's call it P. So P equals n minus 7n to 7n plus 15. Let's see. This equation is hard to work with. Maybe there was a simpler factorization I missed. Let's re-examine the coefficients. 1, minus 14, 64, minus 91. What if I made a mistake in the synthetic division? 1 minus 14, 64 minus 91. Test n equals 7. Drop 1, 7 asterisk 1 equals 7. Minus 14 plus 7 equals minus 7. 7 asterisk minus 7 equals minus 49. 64 to 49 equals 15. 715 equals 105 minus 91 plus 105 equals 14. The division is correct. Pn equals un7n2, 7n plus 15 plus 14. This is a really tricky problem. Let's think about the structure. A prime number p is equal to the sum of two terms. P equals a plus b, where a equals un7n to 7n plus 15 and b equals 14. This doesn't seem to help. Let's try to rearrange the equation.
P14 igual a n menos 7n al cuadrado menos 7n más 15.
This is much better. This means p minus 14 is the product of two integers, n minus 7 and n squared minus 7 north plus 15. Let's analyze the factors. We already know that na7n plus 15 is always positive and its minimum value is 3. What about n minus 7? This can be positive, negative, or 0. Since n has to be a positive integer, n starts from 1. Case 1, n equals 7. If n equals 7, then un7 is 0. The equation becomes p minus 14 equals 0, which means p equals 14. But 14 is not a prime number since it's 2 times 7. So n equals 7 is not a solution. Now, for any other value of n, we have p14 being a product of two non-zero integers. Let's think about primes. A prime number p is an integer greater than 1, whose only positive divisors are 1 and itself. Let's test some values of n. If n equals 1, p1 equals minus 40, not prime. If n equals 4, p4 equals 64 minus 14, 16 plus 64, 491, equals 64225691320315 equals 5. 5 is a prime number, so n equals 4 is also a solution. Let's check with our factored form. 4n equals 4. P minus 14 equals 42742 minus 7 asterisk 415 equals 31628 plus 15 equals 3 equals minus 9. So P14 equals minus 9, which means P equals 5. This also works, so n equals 4 is another answer. If n equals 5, p5 equals 125 to 1425 plus 64 591.